In today's video, we will learn about thermal expansion. We see that thermal expansion is due to the consequence of the increase in the average separation between its constituent atoms or molecules. There are three types of expansions that we will review today: linear expansion, area expansion, and volume expansion. For linear expansion, it's expansion that results in an increase in length of an object. We can calculate the change in our length by multiplying our coefficient of linear expansion, which depends on the material, multiplied by the object's original length, then multiplied by the change in temperature. Area expansion occurs when a two-dimensional object expands. Our change in area of the object can be calculated by taking gamma, which is equivalent to 2 times the coefficient of linear expansion, multiplied by the original area of the object, then multiplied by the change in temperature. Volume expansion occurs when we have an expansion of a three-dimensional object, and we can calculate our change in volume by taking beta, which is equivalent to 3 times our coefficient of our linear expansion, multiplied by our original volume times our change in temperature. If we were to look at our first example, we're given two 12-foot sections of aluminum siding that are placed end to end on the outside wall of a house. We're asked how large of a gap should be left between the pieces to prevent buckling if the temperatures can change by 55 degrees Celsius. And we're given the linear expansion coefficient, which is equal to 23 times 10 to the negative 6 over degrees Celsius for our material of aluminum. If we summarize the information we're given that the length of the aluminum is 12 feet long, and that our change in temperature will be a change of 55 degrees Celsius, and our coefficient of linear expansion is given to us to be 23 times 10 to the negative 6 per Celsius degrees. So if we look at our equation for linear expansion, we see that our change in length is equal to our coefficient of linear expansion times our original length times our change in temperature. Given 3 out of our 4 variables, we can solve for our change in length. If we plug in our coefficient of linear expansion, which is 23 times 10 to the negative 6, multiplied by our original length of 12 feet, then multiplied by our change in temperature of 55 degrees Celsius, we see that our change in length is equal to 0.015 feet, which we can then convert into inches. So for 1 feet, there are 12 inches. Our feet will cancel out, and we'll be left with our answer, which is equal to 0.18 inches. In our second example, it states that the density of gasoline is 7.3 times 10 to the second kilograms per meter cubed at a temperature of 0 degrees Celsius. Its average coefficient of volume expansion is equal to 9.6 times 10 to the negative 4th per degree Celsius, and we're given that 1 gallon is equivalent to 0.0038 meters cubed. And in part A, we're asked to calculate the mass of 10 gallons of gasoline at a temperature of 0 degrees Celsius. So we're given the density of gas to be equal to 7.3 times 10 to the second kilograms per meters cubed. And we know that density is equal to our mass divided by our volume. We're given the density of gas as well as a volume of gasoline in gallons. So if we're trying to solve for mass, we can rearrange this equation where our mass will be equal to the density of gas multiplied by our volume. So given that the density of gasoline is 7.3 times 10 to the second kilograms per meters cubed, and then if we multiply our density by volume, we're given a volume of 10 gallons. However, since our density is in meters cubed, we'll have to convert our volume of gallons into meters cubed. So we see that for 10 gallons of gasoline, 1 gallon is equivalent to 0.0038 meters cubed. And we see that our gallons will cancel out and we'll be left with meters cubed. Now that we can calculate our mass, see that the mass of gasoline will be equal to 27.7 kilograms. And part B, we're asked if 1 meter cubed of gasoline is at a temperature of 0 degrees Celsius and is warmed by 20 degrees Celsius, calculate its new volume. So in part B, we're asked to calculate the new volume. So we can look at our equation for the expansion of volume, which is defined by the equation that our change in volume is equal to beta times our original volume multiplied by our change in temperature. So if we can solve our equation for our change in volume, since our coefficient of beta is given to us, which is said to be equal to 9.6 times 10 to the negative fourth, and that our original volume of our gas is 1.00 meters cubed, and we have a change of temperature of 20 degrees Celsius. When we calculate this out, we see that our change in volume will be equal to 0.0192 meters cubed. So we've calculated our change in volume, but we're asked to find what's the new volume. So we know that our change in volume is equal to our final volume minus our initial volume. So if we are asked to find our final volume, we can rearrange the equation where our final volume will be equal to our change in our volume plus our original volume. Knowing these two variables, we can now solve for our final volume. Our change in volume was equal to a 0.0192 meters cubed plus an original volume of 1.00 meters cubed. When we add our values together, we see that our final volume will approximately be equal to 1.02 meters cubed.